All right, everybody, here's a question I always get, or two questions if you look at it. You've seen me use examples of double switch and single switch. There is a simple sentence that covers both of these, but I will be more specific than that. And the simple sentence I will put ahead of them. And it covers both single switches and double switches. Every time you do a switch, the stereo center switches from R to S or vice versa, the opposite. That's a fact. Both have their uses, people. Both have their uses. I'm trying to move this thing and it's not letting me. Oh, wow. Every time you do a switch, it switches from R to S or vice versa. You do a double switch, when you need to name a stereo center, when you need to name a stereo center, and the number 4 group is not on a wedge. Well, that's different. I thought it was only when it was not on a dash. I'm going to make your life easier. Do one where it's on a wedge. So here's the 2 times you have to use a double switch. If you've got a tetrahedron and the number 4 group is here, or doesn't matter where the other groups are, the number 4 group on the same tetrahedron. I didn't draw that very nice. I should have copy pasted. Here we go. Or the 4's here. The other 2 examples, you don't need it. The other 2 examples being 4 on a wedge already. Circle 1, 2, 3 for answer. And the other one is circle 1, 2, 3 for the wrong answer. Isn't the rule to put the number 4 on a dash? So what's 180 degrees away from a dash, which means you're standing on the wrong side of the molecule. A wedge is 180 degrees from a dash. So if you connect 1, 2, and 3, for example, if 1 was here, 2, 3, and 3 here, here it's clockwise, but when I'm behind the page, it's going to be counterclockwise. So the R is wrong and the S is right. So the only 2 times you have to do a double switch is the 2 non-wedge dash bonds. Okay? And that's when you do it. If it's already on a dash, you'd follow the normal process. 1, 2, 3 gives you the answer. If it's on a wedge, it's just as simple. Follow the process, connect 1, 2, 3. Your answer is wrong, switch it to the other answer, which is right. Bingo. When do you do a single switch? When you want to change the stereo center. This is not nomenclature. Changing stereo centers, not nomenclature. Nomenclature is naming. This is when you want to create the opposite stereo center. Now, in our previous example, that first stereocenter I did was wrong. So I had to fix it to right. And the best way to do it, the easiest way, is just to do a single switch. So here we go. Let's do just a full example here. And let's put a fluorine, a chlorine, a bromine, and an iodine. Unfortunate choice. I'd have to do a double switch to verify my answer. So I'm just going to put the lighter fluorine over here and the iodine here. F. And things are a little messy down here. There. Okay, this one is currently R. Draw the S quickly. Watch this. Same tetrahedron, Cl here, I here, the other two the same. Done. How do I know that's S? Just a reminder here. I know it's all new to us. 127, 89, 35.5, and 19. It's R. I mean, you could do the work over here to verify it's S. It goes like this, which is S. But I did a single switch on an R. I didn't need to verify my work. Okay? And the same story happened when we did our chair. I needed a quick way to redraw this so that the stereocenter here, 1 had to be S because it said so in the name, and currently it was R. So a single switch, another good way to do it is just whatever was a wedge, make a dash. So this wedge is now a dash, and whatever was a dash is now a wedge. That is a single switch. I didn't change anything else. And I got the right stereocenter. I didn't even need to verify it. You're saying, wait, Dr. Whitaker, it doesn't look like it's S. I connect 1, 2, and 3, and it's R. What is it really when the number 4 is on a wedge? 1, 2, 3 is wrong. And we just learned about that right now. If that's wrong, then what is right is S. Clockwise is wrong. Counterclockwise is right. And there we go. We have that. All right. So that's when do we use double switch? When do we use single switch? All that good stuff. When you want to create the opposite stereocenter. Okay, I'm going to leave it up to you to practice this stuff on your own because that's the only way to get good at it. Get on your OWL, get on your textbook. The textbook's got lots of examples and it's got all the answers. So I want you to do that. And I'm looking for something here. Here we go. I'm going to bring over chapter 2, if it lets me. Here we go. And we have physical properties of alkanes we're going to talk about. Do you remember physical properties from your 141 days? We had things like solubility, boiling points, and melting points, and density. And let's look at density while we're here. Density is the ratio of an object's mass to its volume. The most common units are grams per milliliter. And if you don't know already, that a milliliter is also the same as a centimeter cubed. Please learn that now. One problem about doing science in this country where we did not adopt the metric system is that most people don't have a sense of what a milliliter looks like. and they don't have a sense of what a centimeter looks like. And this is dangerous when we're talking about doing things like drug dosage, which depend on the metric system all the time. You're not allowed to make a mistake on a drug dose. I hope you know that. So what object can you use that gives you an idea how big of an object is a centimeter? Well, you take your little finger and you look at the nail going up and down there. And for most people, that distance from the top of the nail to the bottom is roughly a centimeter. So centimeters are about this big by this big, and this big to be a milliliter, centimeter cubed. It's not a big object, is it? That's why in a 1 liter bottle, we've got 1,000 of those. And in a 2 liter, you've got 2,000. Doctors like to call the centimeter cubed a cc, cubic centimeter. So we should know we're talking about milliliters all the time here. And also in this country, nobody really has an idea what a gram feels like in your hand. Well, how much does that weigh? It's not a lot. A good object to keep in mind is, I don't even know if it's written on here. I don't know, it should be somewhere. It's been a while since I wrote this, but just remember. Oh, it says right there. I don't have one on me. A nickel. It only works for a nickel, does not work for dimes or quarters. A nickel is good because if you put it on the balance in the lab, it comes out to almost exactly 5 grams. That's easy to remember. What does 5 grams feel like? It feels like you're holding a nickel. 5 cents. Okay, so grams aren't very big. They're a fifth of a nickel. And milliliters aren't very big either. And there's one density I hope you've memorized for the rest of your life, and that's the density of water. And what is the density of water? 1 gram per milliliter. A lot of the metric system is based on water, right? That's nice because it's everywhere. So we're talking about chapter 2, alkanes, which are saturated hydrocarbons. And we've had several spills of alkanes in our history since we're so dependent on oil. We get oil out of the ground and we have to transport it all over the world so we can refine it, so we can put it in our cars for running around town. We can put it in our homes for home heating fuels. If you live on the East Coast, that's very popular. Or you can go up north and heat your home with propane. And all of these are hydrocarbons, and when they spill in water, they float. Why? Because they have a density less than 1 gram per milliliter. So you need to know that. They float. Density less than 1. Hydrocarbons do not like dissolving in water. We're going to spend for the rest of, I think we'll just do physical properties for the rest of the day. Hydrocarbons, they don't dissolve in water because they're nonpolar. You can't have a molecule that has only nonpolar bonds be polar. And hydrocarbons have bonds from carbon to carbon, and they have bonds from carbon to hydrogen. That's all they have. None of those bonds are polar. Water is very polar. It's got a polar covalent bond between OH one direction and in the other direction, and the lone pairs push them together so it's bent, and it's that bent shape with the 2 dipoles not canceling each other that gives water its very severe polarity. So hydrocarbons don't dissolve in water because nonpolar molecules like associating with other nonpolar molecules. So they will stay together, the hydrocarbons, and the water likes to associate with other polar molecules like water, and they will stay together and they will not mix, like oil and water, like Italian dressing, right? Okay. So they don't dissolve in water. Now let's talk about intermolecular forces, because they tell us things like how high a boiling point is and how high a melting point is. If you've got strong intermolecular forces, you're going to have higher boiling and melting points, all right? If you have very weak intermolecular forces, you're typically going to have a gas molecule. A little stronger, it's going to be a liquid. Very strong, it'll be a solid. Our weakest intermolecular force, sadly, we have people putting their names on things. This isn't even the saddest part of this discussion. I do not like people's names on things. They don't trigger my memory. London does not say nonpolar to me. The Dutchman van der Waal, that doesn't say nonpolar to me. Dipole, I like the name of that one. That's real good. That shows if I have a polar covalent bond, it will be attracted to another polar covalent bond so that the plus portion is right next to a negative portion in another molecule. There's an attraction there, right? Intermolecular means forces between different molecules. These are not to be confused with bonds, which brings up the worst mistake ever in naming something right here. Right after the teacher says you're not to confuse intermolecular forces with bonds, some people named one of the intermolecular forces with the word bond in it. This was terrible. This should have never happened, and it confuses students to this day and will until they change the name, which probably won't happen. A hydrogen bond is not a bond. It's an intermolecular force. And we'll go through each of these, and we are going to, in our discussion, only talk about dipole-dipole forces. In molecules that have only nonpolar bonds, we have to rely on the fact that electrons never sit still. They are always moving back and forth in a bond. So in this picture over here, I have this bond at this given instant in time. The electrons moved away from the carbon towards the hydrogen. And it's changing all the time. I know it goes against electronegativity, but they're almost the same electronegativity. So at this given instant in time, we have a temporary dipole where the electrons happen to be closer to hydrogen. That makes the hydrogen feel slightly negative. At this particular instant in time, in this bond where the electrons are closer to hydrogen, carbon feels a little bit positive. If there's another methane molecule, which is what this is, it will align itself to take advantage of that. If it has a similar temporary dipole, it's going to put its slightly negative hydrogen underneath the carbon here, and this slightly positive carbon underneath the hydrogen here. And these dipoles are temporary. What do we call a temporary dipole attraction between molecules? Notice I use the word dipole, not London, not van der Waal. We should have called them temporary dipoles from the beginning. Yes, it's a little longer a name, but it actually says what it is. Okay. And here's my two molecules. If you can just pretend those two dots are one of my hands and the other two are my other hand, and the molecules will always be above and below each other, but the dipoles will be doing this, moving towards the other atom. So there's always a plus above a negative or a negative above a plus. And they're constantly fluctuating so that the molecules can take advantage of these temporary attractions. These, as you know, are the weakest intermolecular forces. Never are these very strong attractions. They're very weak, and they're always changing. Okay? So molecules that have only London forces, which are really just temporary dipoles, have low boiling points typically, not always. If you have very large molecules, you have lots of electrons, don't you? So even if the forces individually are weak, if you have lots of carbons and hydrogens, those forces can add up. And then you get molecules like wax. Wax is hydrocarbons. It's a solid. How can it be a solid? Well, it's got very big molecules with lots of tiny London forces. They add up to be substantial. So normally when we're comparing intermolecular forces, we should compare molecules with similar size so that the only variable is the nature of the intermolecular force. So when I switch to different intermolecular forces, I'm going to pick molecules that have a mass of roughly 30 grams per mole. So I'm going to switch to ethane in the discussion here. Ethane has a boiling point of -89, and that's a lot higher than methane, -164. Why? It's got more electrons that have temporary dipoles, so it's more London forces. -89, though, is still a very low boiling point. Formaldehyde has almost the same mass. It's within 2 grams per mole. It's depicted here. And based on your knowledge of electronegativities, you know carbon with a 2.5 and oxygen with a 3.5. There's a difference of 1.0 there. That is called a polar covalent bond. Molecules with polar covalent bonds are attracted to other molecules with polar covalent bonds, and the attraction is called a dipole-dipole attraction. And it's not a temporary dipole, that's a permanent dipole because of the electronegativity differences between the atoms. How substantial is this? Well, you took something that was ethane with a boiling point of -89, and just by having one polar covalent bond, it jumped by more, let's call that -90 and -20. That's a jump of 70 degrees Celsius. That's a huge difference. Why is it so different? Much stronger intermolecular forces. Okay, now I'm going to switch over from formaldehyde to methanol, which only weighs 2 grams per mole more. So the size of the molecule is pretty much the same. Yet we jumped up by another, let's see, we went -20. Can we call that close to 70? That's a 90 jump. That's a big jump again. Why? I don't want to use the name of this intermolecular force. I'm going to rename it. This hydrogen being bonded to a very electronegative oxygen, there's two things going on. The polar covalent bond is even more polar because the difference here is 3.5 minus 2.1 is 1.4. That's even a bigger difference between these two is 1.0, but that's only a small part of the story. The other part of the story is, yeah, you got a hydrogen that's very positive because it's bonded to an O. And hydrogen, just by its very nature, is the smallest element, which means it can get closer to other molecules. It's so tiny, it's easy to sneak it into close to another molecule, which makes hydrogen bonding a pretty profound intermolecular force with a very bad name. Let's just call it an extreme dipole-dipole. How's that? That's what they should have called it. Extreme dipole-dipole. Not every hydrogen qualifies. These hydrogens attached to carbon do not qualify for hydrogen bonding. They're not in a polar covalent bond. Do you remember the 3 atoms that hydrogen must be covalently bonded to so that they can participate in an intermolecular hydrogen bond with another molecule? The 3 elements were oxygen, depicted here, fluorine, depicted in only inorganic chemistry. You know why? The molecule, the only possible molecule, is HF. Is that organic? No. So we don't talk about HF in this course. You're restricted to molecules that have H bonded to O and H bonded to the third one. Do you remember? Do you remember? Nitrogen. And since we're learning organic chemistry now, let's review the functional groups that can participate in hydrogen bonding. The functional groups, hello. The functional groups that can participate in hydrogen bonding. And you know, Dr. Whitaker doesn't like that name. Extreme dipole, intermolecular. Well, I didn't have a typo there. That's amazing. Forces. All right. There's not a lot of them. We need molecules that have a functional group that has O bonded to H or N bonded to H. And if you think there's just like 2 or 3, then you're not being specific enough. What do I mean by that? Well, don't just say alcohol. Say the 3 types of alcohol, or 4 really. Alcohols, primary, secondary, tertiary, and there's one where the carbon has no bonds to other carbons. It's called methyl. So we got CH3OH, which was the example in the text. And we could do a tertiary alcohol here. There's examples here. We have carboxylic acids. So 5 functional groups. 4 alcohols and carboxylic acids. How about carboxylic esters? They will not be appearing on this page. Why not? The carboxylic ester doesn't have H bonded to O. Amines, but not all of them. Primary, yes. Secondary, yes. Tertiary, no. If you have a primary amine, let's do examples over here. Carboxylic acid, there's a short form. Primary amine, we can do ethanamine. Secondary amine, we can do dimethylamine. I'm going to cross this one off. Here's a popular tertiary amine. Doesn't belong. No NH covalent bond. So that molecule cannot hydrogen bond with itself. That one is tertiary. It's not on the list. Similar story for amides. Amides. In fact, a lot of you have studied a little biology, and you know the alpha helix of a polypeptide, also known as a protein. Its shape is largely held by hydrogen bonding. Some of you don't know what I just said, which is just fine. Don't even worry about it. So we have amides. You got your primary. That's that one. And your secondary. But you get rid of that H to get a tertiary. I'll draw it here and cross it off. And crossed off for the exact same reason as the other one. And that's tertiary. Put it in a little yellow box. We're running out. It's pretty good. So I think you want to look ahead at the problem. The exam question is going to go like this. Put the following 7 molecules in order of increasing boiling point. And you're going to have to discuss intermolecular forces for sure. And look at all the practice ones you can find. They don't always show up on test 1. When you get the study guide, I think I'm going to direct you towards spring 19 where it did happen. And if those problems don't occur during test 1 of any semester, the odds are very high that the test 2 with the same semester name will have the boiling point in order question. And you will be having that this semester. Study guide coming very soon. The sooner I can get that to you, the better. I think I'm almost done with it. I may get it to you tonight because it's good to know what to expect. And I'm sorry about the video that you're going to have to wait for. I believe it's segment 2 from today. I will post the rest of them during lunch. I'll try. And I look forward to seeing you Wednesday, and take care of yourselves. Make sure I save this one properly.